A thread thinner than hair just stopped a fast-moving insect without breaking under extreme force.
Despite the impact, the web absorbs the energy, redistributing force across its entire flexible structure.
How can something nearly invisible outperform materials humans have engineered for centuries, like steel? Steel is strong, but under sudden stress, it can fail abruptly without absorbing much energy. Spider silk behaves differently, stretching significantly while maintaining integrity instead of snapping under pressure. This extraordinary material is produced naturally by spiders through an advanced biological process refined over millions of years.
Inside the spider's body, specialized glands produce proteins that are transformed into silk as they exit.
These proteins organize into long molecular chains that define the silk's strength and flexibility at microscopic scale. Rigid crystalline regions provide strength, while flexible chains allow the material to stretch under sudden forces.
This hybrid structure enables spider silk to absorb energy efficiently, preventing sudden failure during high-speed impacts.
Interestingly, spiders can move freely across their webs without getting stuck, thanks to specialized, non-adhesive pathways. To us, spider silk feels fragile, yet even a human cannot easily break its elastic structure instantly.
Multiple strands working together can support surprisingly large loads relative to their microscopic size and weight.
In laboratory conditions, scientists measure spider silk as one of the toughest biological materials ever studied. When disturbed, the silk vibrates, spreading energy across the web like a finely tuned mechanical system. Energy travels along the silk as waves, preventing localized stress and reducing the chance of catastrophic failure.
Even in strong winds, spider webs can survive repeated stress without tearing apart completely.
Unlike brittle materials, spider silk stretches and dissipates energy instead of snapping under sudden pressure.
Spiders also use silk actively, wrapping prey quickly with precision and efficiency during capture.
This delicate structure is not just a trap, but a highly optimized engineering system shaped by evolution.
Scientists have long been fascinated by spider silk, attempting to understand and replicate its extraordinary mechanical properties.
Under magnification, silk reveals a complex hierarchical structure that contributes to its exceptional strength and flexibility. Proteins align and fold in precise patterns, forming fibers that combine crystalline strength with elastic molecular chains.
Despite advanced technology, reproducing spider silk artificially remains extremely difficult due to its complex natural production process.
Nature still produces stronger and more consistent silk than most artificial methods currently available to scientists today.
If replicated successfully, spider silk could lead to ultralight protective materials stronger than conventional armor systems. In medicine, silk-inspired fibers could be used for sutures that are both strong, flexible, and biocompatible.
Engineers imagine using similar materials for cables that are lighter, stronger, and more energy efficient.
Meanwhile, in nature, spiders continuously rebuild and repair their webs using the same remarkable material.
Without machines or tools, this tiny creature produces a material that challenges human engineering capabilities.
A single strand of spider silk contains millions of years of evolutionary refinement encoded within its microscopic structure. Under tension, the silk stretches dramatically, absorbing energy while maintaining its structural integrity without immediate failure. While steel fractures suddenly under stress, spider silk deforms gradually, distributing forces before reaching its breaking point. This flexibility allows the web to survive repeated impacts, capturing prey while maintaining its overall structural stability. Even under harsh environmental conditions like wind and rain, the web absorbs stress without collapsing or tearing apart.
At the center of this system, the spider relies entirely on silk for survival, sensing every vibration with precision.
Every strand plays a role, forming a network optimized through natural selection across millions of years. Across ecosystems worldwide, spiders quietly build structures that rival the efficiency of many human-engineered systems. For scientists, spider silk remains one of the most intriguing materials still not fully understood.
Its properties continue to inspire research into stronger, lighter, and more adaptive materials for future technologies.
From a tiny organism emerges a material that challenges our entire understanding of strength and engineering.
What appears fragile at first glance is, in reality, one of the most advanced natural materials ever created.
Perhaps the future of engineering lies not only in invention, but in learning from nature's existing designs.
In silence, this small creature continues to build with a level of precision we are only beginning to understand.
Sometimes, the greatest engineers on Earth are not human, but hidden within the smallest forms of life.